Where we are now is we are still getting into some of the tools we need in 3 dimensions. So we already talked about points in 3 dimensions. Well, a coordinate system, a three-dimensional coordinate system, and then how to represent points based on various distance from the coordinate planes. And then we're now into representation of vectors in 3 dimensions. We talked a little bit about how to do some algebra on vectors. In particular, we looked at the dot product, which was a way to determine whether two vectors were perpendicular or not. And in fact, what the dot product of two vectors told us in some sense was how much the vectors point in the same direction. And we used it to get this idea of a projection of one vector onto the other. And then we're getting now into the cross product, which is another way to combine two vectors. Unlike the dot product, which takes two vectors and produces a scalar, the cross product takes two vectors and produces another vector. And this is only in 3 dimensions. So let's look again at the motivating problem for the cross product. The idea is we've got two vectors. They form, or they can form, some sort of parallelogram. And that parallelogram has an area, which we'll call A. And we'd like to know how to determine the area of that parallelogram. How can we compute it? It turns out that if we know the two vectors, maybe I think last day I might have written it B on the bottom and A up. So I'll continue with that. If we know the two vectors, then, and we know the angle between them, then we can work out the area by just working out what the height is. So what is that height? And what is the base length? Because the area of this parallelogram is just equal to the area of the corresponding rectangle I get by sort of shifting everything over, shifting all the layers over. And in this case, the height is going to be the magnitude of A sine theta. The width is the magnitude of B. So in that case, the area is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. And so that's how we can compute the area. But what this means is we need to know what the sine of the angle between the two vectors is. We know how to find the cosine of the angle. So we could, in fact, use the dot product to find the cosine of the angle and then take arc cosine to find the angle itself and then plug it into the sine function and work out this value and get the area ultimately. But we're going to have a better way to do that. Instead of actually finding the angle, we're not going to have to worry about the angle at all, but we're going to come up with a different way of being able to determine this area. And that's related to this product known as the cross product. So for two vectors A and B, we define the cross product to be this vector with 3 components, where each of the components is built up from the components of A and B. Now, you may look at this product and say, okay, am I supposed to remember that? And the short answer is yes. The slightly longer answer is we have a way to remember this product, and it relies on knowing a determinant. And so we can build this product up as a determinant in the following way. So here's how to remember the formula, how to remember cross product. So how do we do that? Well, what we do is we take, so if I'm looking at A cross B, what we do is we form a matrix which has I hat, J hat, and K hat as these entries in the first row. And so this is just a memory device because I'm forming a matrix, but in this matrix, I'm taking my first row to be vectors, and then my next couple of rows will just consist of scalars. So it's not really an object we're we're used to dealing with. And so this is really just a memory aid. And then so for the next row, I write down the components A1, A2, A3, and the next one I write down B1, B2, B3. So I form this quote unquote matrix with the second and third rows being our vectors and the top row being the standard basis vectors. And this vertical bars, these mean determinant. So we're looking at a determinant here. And if you've already done linear algebra, you know about determinants. If you're currently in linear algebra, you will, if you haven't already, you will get to determinants soon enough. And so what this becomes is, to compute the determinant, we just expand across the first row. And what we end up doing is we take the determinant of the second and third columns, but just the last two rows. So this little block, I'll indicate it down here. So we take this guy and we multiply it by the determinant of the remaining entries, which I is not in the row or column of. And so there's going to be an I hat here. And then we take away from it. So we got this alternating sum happening here. This guy multiplied by the determinant of the remaining 2 by 2 matrix, which is that one. So this is A1, A3, B1, B3, multiplied by J hat, and then plus the remaining one with the K hat. And so that's going to be A1, A2, B1, B2, and K hat. So that's our memory device. Works well if you've already seen determinants, because now we do the 2 by 2 determinants are as follows, where the 2 by 2 determinants are, so for example, I'll do this one, B2, B3. You take the diagonal elements and multiply them together, which are A2 and B3, and then you take the opposite diagonal elements and multiply them together and take their difference. And you can see that that's precisely what's sitting here in this first entry. It's A2B3 minus A3B2. And then the next entry is just that determinant of the A1, A3, B1, B3 matrix. But with the negative sign in front means that our terms are switching. So however you want to remember it, I encourage the matrix form if you're familiar with matrices, and if not, it's you're taking linear algebra this term then, most likely, because it would be a prerequisite. And so you'll learn about matrices and determinants soon enough, and that'll help you remember the cross product formula. We'll do a few calculations in a second, actually computing cross products, but let's see what kind of properties we want the cross product to have. So there's really two main properties we want the cross product to have. It's defining properties. So the idea is, suppose I've got two vectors A and B. What I want to do is I want to construct a third vector from those, and I want the properties of that third vector to be that it's orthogonal to both of the original two vectors. So it's orthogonal to both A and B. And being that it's orthogonal, it's going to have two directions. It's either going to point up or down in some sense. If we think about the picture down below, I've got A and B, and I've got a vector that's perpendicular to them. It's either going to be the one that's pointing up as shown, or it's going to be the one pointing in the opposite direction. Those are our two possibilities for a perpendicular vector. We want to choose the one that's obeying the right-hand rule, so that if I point my fingers in the direction of A, curl them in the direction of B, my thumb of my right hand is pointing in the direction of the cross product. So that's our first defining property. We want this new vector to be orthogonal to A and B and have a direction given by the right-hand rule. That itself already tells you that the order in which you take a cross product matters. Because if I was to take B cross A, then the right-hand rule tells me it would point in the opposite direction of A cross B. So that right there tells us already that the order in which I take this product matters. The other property we want, so now we know the direction, we need to know the magnitude, and the magnitude is going to be given by the area of the parallelogram defined by A and B. So if A and B defined a large parallelogram, then the vector will be really long. If A and B define a very small parallelogram, then the vector would be very short. So that gives us our direction and our magnitude, and those are the two defining properties. And it turns out that if you want a vector that has these two properties, given from A and B, given that is constructed from A and B, then the components have to be given as they're stated there. It's got to be these mixed products. So this formula gives the components of such a vector. Now what we'll do is we'll argue the following. We'll say, okay, given A and B, if I construct a vector using this formula, then we will show that it satisfies these properties, that it is orthogonal and has the correct magnitude that we wanted. So let's just go ahead and compute some cross products. So we're going to find the cross product of these two vectors. Okay. I'll put a little memory device up here. Sometimes you're able to do it just, well, if you do it enough times, you won't even have to write down this particular array. You'll be able to do these products in your head. But our memory device tells us that to get the first entry, what we're going to do is we're going to multiply these two and those two and take their difference. So it'll be 7. Oh, sorry, I wrote down a 0 and it should have been a 3, 4, 2. Okay, so this is going to be 7 times 2 minus 4 times 0. Our next entry we get is we're going to multiply the 5 and the 2 and the -3 and the 0. But in this case, we're going to take negative of that result. So this is how I like to remember. We're going to do that same multiplication, but there's going to be a negative sign thrown in front. So it's 5 times 2 minus -3 times 0. And then the last product we're going to do is the 5 times 4 and the minus -3 times 7. So that's 5 times 4 minus -3 times 7. So those are our 3 components, and now we can work out their values. The first one is 14, the next one is 10 negative, so minus 10, and then we've got a 20 plus a 21 or a 41. And so those are our values in this case, our components, 14, -10, and 41. Okay, so this is the cross product. This is how we're going to work it out. Now, if you do enough of these, if you get some practice, if this is new to you and you get practice, you'll be able to go from here right to there for small numbers, for numbers that you can sort of work these values out in your head, usually in one step. But for the first few, get practice with writing out your memory device just so you get all of the proper signs and the proper products. The next thing we want to do is we want to show that if you take a vector and you cross it with itself, then you're going to get 0 for any vector. So let's take a look at that. A cross A is equal to, and we'll go ahead and we'll write out what the product is. So it's going to be A2, A3 minus A3, A2. And then in the next one, it's going to be A3, A1 minus A1, A3. And then the next one's going to be A1, A2 minus A2, A1. So that's our definition of the cross product with A1, A2, A3 plugged in for both the A and the B vectors. And we see that this is just going to be a bunch of zeros because all we're doing is taking a product and subtracting off the product in the opposite order. And this is just products of real numbers. The real number multiplication is commutative, so this is 0, 0, and 0. So when you read an expression like that, so I show that A cross A is 0, we should keep in mind that we know these are vectors already. A and A are vectors, and the cross product does produce a vector. So this is the 0 vector sitting there. So that was a boldface type, but as I mentioned before, I'll try to put the arrows in on top for handwriting purposes, just so you can see that these are vectors without having to decipher whether it's boldface or not. The question was, shouldn't the middle term be multiplied by -1? It actually is, because if you look at the way I did the order here, is I'll do this again. A1, A2, A3, A1, A2, A3. What I end up doing to get that middle term was I took the product of these ones first and then multiplied by the product of these ones. But they are the same term. So it might be hard to see, but yeah, there was a -1 factor that was sitting in there. Okay. So that tells us that the cross product of two vectors, or a vector with itself, is 0. That actually, if I back up, that actually puts a little bit of emphasis on this one. Oh, not that one, the second one. Puts a little bit of emphasis on this one. We want the magnitude to be equal to the area of the parallelogram defined by the two vectors. If I took a vector A and crossed it with itself, then the magnitude of the resulting vector should be the area of the parallelogram determined by A and A. But A and A wouldn't determine a parallelogram, they just determine a straight line because they're two vectors pointing in the same direction. So that actually adds some emphasis to that last point, that the magnitude of this vector should be the area of the parallelogram, and in this case, that parallelogram would have area 0. The other point is that the cross product of two vectors has to be perpendicular to both A and B. So this is, I'm not going to do it here. I can leave it for you to do, but I will justify it in a way using determinants. But this is, if you want to work this out, this is a straightforward check from the formula. So what would we actually check? Well, we would find the cross product of the two vectors. And then what we do is we take the dot product. And if A cross B is supposed to be perpendicular to A, we should get a value of 0. And so we could check that. We could very simply check these things by just working out the formula for the cross product, which is the definition of the cross product already gives us a formula, and then we just dot it with the various vectors and get the appropriate zeros. Or from our memory aid, what we are interested in is, maybe I'll look at something like this. If I wanted to do A cross B dot A, then from our memory aid, if we sort of work this out, we would do the cross product for A and B, and then we'd have the I hat, the J hat, the K hat, which sort of separates our components. And then we would, in some sense, just be plugging in the components A1, A2, A3 in for I hat, J hat, and K hat. So this would turn out to be equal to the determinant of this matrix here. So that's what it would be. If you worked out what this cross product dotted with A is, it's really just the determinant of this thing. And the point is that these are the same row. And if you have a matrix where you've got rows that are linearly dependent, then the determinant would be 0. So that's another way to think about this in terms of our memory aid, linking it with determinants. But if you haven't seen determinants before, that might be a little bit over your head, so not to worry. There is just that straightforward check right here. Just do that straightforward check and you can find that these are equal to 0. So the cross product is perpendicular to both A and B. That's what we wanted it to be, and so there's a check that our formula does indeed produce such a vector. So let's go ahead and now start to play with these ideas. So we've got our definition of our cross product. We've got these basic properties. Let's do a bit of play with them. Oh, it looks like some people are keeping their eye on the news, so the inauguration is going off, it looks like. Okay, so find a vector perpendicular to the plane that passes through these 3 points. So the idea is we've got this plane in space, and we've got 3 points on it. So 1, 2, 3 is the first point. We've got another point, which is 1, 0, 1. And we've got another point, which is 2, 1, 1. And I want to find a vector that's perpendicular to the plane that passes through these 3 points. So I want to find a vector that's perpendicular. So if I want to find a vector that's perpendicular, what I could do is I could say, well, if I can find 2 vectors in this plane, then I could take the cross product of them, and that would give me a vector perpendicular to those 2 vectors, and therefore a vector perpendicular to the plane. So the first thing I'm going to do is construct 2 vectors in the plane. So maybe I'll take these 2 vectors. So I'll call this one, let's say, A, and this one B. So A is going to be the vector given by the tip 1, 2, 3 minus the tail 1, 0, 1. So 1, 2, 3 minus the tail 1, 0, 1. And so that's our vector 0, 2, 2. And B is going to be the vector given by its tip 2, 1, 1 minus, oops, okay, space that out, minus the tail 1, 0, 1. So that's 1, 1, 0. So those are our 2 vectors. Now we want to compute the cross product of them. So if I go A cross B, that's 0, 2, 2 cross 1, 1, 0. And what's our cross product going to be? We can use our memory device to help us set up these products. So that's 0, 2, 2, 1, 1, 0. So our first product is going to be 2 times 0 minus 2 times 1. So that's going to be minus 2. Our second product is going to be 0 times 0. So maybe I should say negative 0 times 0 minus 1 times 2. So that's going to be negative, negative 2. And our last one is 0 times 1 minus 1 times 2. So it looks like it's negative 2, 2, negative 2. And so that's our resulting cross product. And what we end up getting is that this is supposed to be a vector that is perpendicular to the plane. The question is, which direction is it pointing in? The direction that it's pointing in is in the direction given by the right-hand rule. So we took A cross B. So if I point my right-hand fingers in the direction of A, curl them in the direction of B, it means that it's pointing up in this direction. And so there's a right angle there, and right angle there. And that's our vector, negative 2, 2, negative 2. Now, whenever I do a calculation like this, and I encourage you to do the same, you got this cross product. There are many places that you can drop signs or introduce an extra sign or take the difference wrong, that it's always a good idea just to do a quick mental check. This thing's got to be perpendicular to the original two. So checking perpendicular, checking two vectors are perpendicular is just a simple matter of doing a dot product. So what I would suggest is just check, is the dot product of that and that 0? And is the dot product of that and that 0? So check the dot product. So if we do it with the vector A, yep, we got 4 minus 4 is 0. We do it with the vector B, we get -2 plus 2 is 0. Yeah, so it is perpendicular in this case. Okay. Now let's do the final connection with the area of the parallelogram. Did I get should it be a -1? That's a good question. So for that last component is going to be obtained by taking this product, 0 times 1 minus 1 times 2. So there's a -2 there. So it looks like -2 is fine. Okay, so here's our fact. If the angle theta is between the two vectors A and B, then the magnitude of the cross product is the magnitude of the two vectors times the sine of the angle between them. So I'm going to sketch why this is true. So sketch of proof of this. The proof is just a heavy algebraic calculation, but I just want to point you in the direction of what the calculation would be that we would perform. So here's what we would do. We would say, take the cross product, which is the thing we're interested in sort of reducing. But in fact, we want to talk about the magnitude of this thing. We want to show that that's the magnitude of the two vectors times the sine of the angle between them. So I want to look at the magnitude of this. But it's easier to work with the magnitude squared, because when I do a magnitude, I've got to take the square root of the sum of the squares of the components. So I'm going to work with the square of the magnitude, because that eliminates having to work with square roots. So what is the magnitude squared? Well, that is the dot product of the vector with itself. And we know what the components of A cross B are. That's given by the definition of the cross product. So this works out to be, it's A2 B3 minus A3 B2 squared plus, and then the next component, which is what's our next component in our cross product. So if we're thinking of in terms of the memory aid, we're ignoring the middle column, which consists of the A2 and the B2, and we only are using the X components and the Z components. And so it's going to be, it's the negative of A1 B3 minus, so maybe I'll throw a negative sign in there, negative A1 B3 minus A3 B1 squared. And so that negative really doesn't matter because I'm squaring it anyways. And then we've got the last component, which is A1 B2 minus A2 B1 squared. Okay, so we've got this expression that we can then square, expand it all out. We get a whole bunch of terms. So I am going to just indicate what's happening here. We're going to do some algebra. What's the algebra? Expand and recollect. If we expand it all out and then recollect it in a sensible way, the way we can recollect it is we can collect the terms so that they are equal to this expression. the textbook has the full details of this algebra. So if you want to try your hand at it yourself and can't seem to get it to work out, you can always have a look at the textbook where the full details are. And so then the last one is this, a3b3 squared. So we can get it in this form. An alternate way to say this is if I expanded that expression in the first line and I expanded this expression I just wrote down, then they'll expand to the same thing. There's going to be, an a1 squared, b1 squared term. There's going to be all of these terms that start to appear in both expressions that are the same. So they're going to equal each other. Now, once we've done this, then the observation is that these are just two magnitudes sitting here. This is a magnitude of a squared, and this is the magnitude or the length of the vector b squared. And that last expression is the dot product of the two squared. And so what we have is an equation that's relating all the things we know about vectors. The vectors themselves, a and b, the magnitudes of those vectors, the dot product of those vectors, and the cross product of those vectors. They're all combined together in this one equation. And so that's sort of a nice equation that tells us how these things all relate to each other. And then we can continue on. We know that the dot product is given by the magnitude of A times the magnitude of B times the cosine of the angle between them. But this is being squared, so I've got squares on all of these things. So that's our relationship between the dot product and the cosine of the angle between them. Now I have these common magnitudes, squares, in both terms, which I could factor out. And I'm left with a 1 minus cos squared, but that's a sine squared using a trigonometric identity between sine and cosine. So that becomes a sine squared theta. And so what I have is that the square of the magnitude of the cross product is equal to, oops, I dropped the square on the b magnitude, is equal to the square of the magnitude of a, the magnitude of b, and the sine of theta. So now I can take square roots. Taking a square root, we get that the magnitude of a cross the magnitude of b is equal to the magnitude of a times the magnitude of b times the square root of sine squared. Now the square root of sine squared is the absolute value of sine of theta. But we know that sine of theta is positive. So the square root of sine squared is just sine theta. I can drop the absolute value. And that's since sine theta is, it's positive, or it's a non-negative, I should say, because it could potentially be 0. Why do I know that the sine of theta is strictly greater than or equal to 0? Well, that's because I know something about the angle between the two vectors. The angle between the vectors is between 0 and pi. So if it's between 0 and pi, or 0 and 180, then the sine of those angles is positive. So that's because theta is between 0 and pi. So that was just how do we avoid having the absolute values around the sine theta? Well, we know it's positive because the angle measure is between 0 and pi. So that is our final expression, which tells us that the magnitude of the cross product is determined by the magnitude of the two vectors and the sine of the angle between them. And that also, much like the dot product, told us whether two vectors were perpendicular or not, depending on if the dot product was 0. We also get a similar result for the cross product. The cross product, if it's 0, it tells us that two vectors are parallel to each other. And so that's because A and B are parallel if and only if the angle between them is 0, they point in the same direction, or pi, they point in opposite direction. But that's precisely the two values for which the sine is going to be 0, which tells us that I should write it this way, which tells us that the magnitude of A cross B is equal to 0. And if the magnitude of a vector is 0, then the vector itself had to be the 0 vector. And so that's our line of reasoning there. So the magnitude of the cross product being 0 tells us that the vectors are parallel. The dot product being 0 tells us the vectors are perpendicular. That's a nice relationship that we have about the geometry and the values of the dots and the cross products. The last thing we have for facts is that the length of the cross product is equal to the area of the parallelogram. And that we already saw. I mean, we already know this result now just because we already stated that if this is A and this is B and this is the angle, then this height here would be the magnitude of A times the sine of the angle between them. And so the area would be the magnitude of A times the magnitude of B times the sine of the angle, and that we know is the magnitude of the cross product. So the magnitude of the cross product is the area of the parallelogram. So that now allows us to calculate things like the following. Find the area of the parallelogram determined by these two vectors. So I've got this vector, let's say 3, 0, 4, and I've got this vector 0, 4, 3, and I'm interested in the area of the parallelogram that they make. And so the area is just going to be the magnitude of their cross product, 3, 0, 4 cross 0, 4, 3. And so we can go ahead and work out what their cross product is. Their cross product is going to be 0 times 3 minus 4 times 4, which is 16. The second term I get is a negative of 3 times 3. So again, I'll write the memory device because it's sort of helpful, but I'm going to do it in my head here. We might as well write this down. So for the second term, we're imagining crossing out this middle one and just going the 3 times 3 minus the 0 times 4, and we're going to take negative that result. So that's a negative 9. And then the next term is we cross out the last column and we take this product, 3 times 4 and 0 times 0. So that's going to be our 12 there. And that's the vector we want. Now we compute its magnitude, so that's going to be the square root of 16 squared plus 9 squared plus 12 squared, which whatever that turns out to be, let me just look it up. That's square root of 481. So that's going to be the area of our parallelogram, square root of 481. Okay. So the nice thing here is we have a product that we can compute, and it gives us geometric information. In this case, it gives us areas. Below I list the properties of the cross product. So these are the algebraic properties that will help us when we're doing any calculations involving them. It helps us replace some cross products with other cross products or do distributions and whatnot. So the properties are, if you reverse the order in the cross product, then you introduce a minus sign, and that's just because the direction is going to be opposite. If you scalar multiply one of the vectors in the cross product, that's equivalent to doing the scalar multiple of the other vector or just scalar multiplying the resulting vector. So in other words, in that second line, the C can appear on any of the two vectors or just around the outside. Cross products distribute across a sum. And the next line, the fourth line, tells us that you could do that on either side. So if I've got a sum A plus B and I take its cross with C, then again, the cross product distributes across the sum. These three here are known as the bilinear properties. So it means if we're thinking of the cross product as a function, takes two inputs and produces an output, then it's linear in each of its two components. The second to last one is known as the scalar triple product. So scalar triple product, and it's a product that involves three vectors. That's the triple part of it. Why is it a scalar triple product? Well, because the result is a scalar. The B cross the C is a vector, and then when you dot it with A, you get a scalar number, or a scalar. You get a number or a scalar, and so that's a scalar, that result. And turns out that the scalar triple product can be computed. It's A dot B cross C, or it's A cross B dot C. So you notice the vectors appear in the same order, A, B, and C. It's just the order in which the dot and the cross product are being done. You can interchange them and you get the same result. And then the last one is our vector triple product. And this one, I'll have you look at investigating on the next homework assignment 2. So that says that the vector triple product is related to a couple of dot products and a linear combination. Okay, so let's do a couple more examples here. The triple product, this scalar triple product that we had, C dot A cross B. That has a geometric interpretation in that the magnitude of it is the volume of the parallelepiped. So if I have the three vectors, A, B, and C, then they construct what is known as a parallelepiped, or sort of a three-dimensional version of the parallelogram. And that object has a volume. And the volume can be calculated by taking that scalar triple product, C dot A cross B. Now, why is that the case? Well, it's sort of given here in the picture in that the volume is going to be equal to the area of the base times the height. Just like a rectangular box. This one's a skewed one, but it's still the same calculation applies. Find the area of the base and then multiply by the height, and that gives you the full volume. What's the area of the base? That's the magnitude of A cross B. What's the height? That's that vector C times cosine of theta in this case. And so then that should be magnitudes in all these cases here. And that is the formula for the dot product, essentially. There's an extra absolute value sign around the cosine theta, but this is effectively the dot product of C and A cross B with the extra magnitude on there because it's supposed to be a positive quantity, and so that's where that positive or magnitude of the cosine comes in. So it turns out that this scalar triple product gives us the volume of the parallelepiped. So let's do an example of this. We're going to use the scalar triple product to determine whether these 4 points lie on the same plane. So what I'll do is I'll just draw a little picture here. We've got our point P, and then we've got these 3 other points. And I'll draw the vectors from P out to them. So we've got S, Q, and R. And I'd like to know if all 4 of these points lie on the same plane. Well, if all 4 points lie in the same plane, then they wouldn't form a three-dimensional parallelepiped like this. Imagine the tip of the vector C actually living in the plane down below. Then it means all 3 vectors lie in the same plane, And if I compute their scalar triple product, I should get a 0 because that would be the volume of the resulting solid, and the solid would just be flat. It wouldn't have any volume. So in order to determine whether these things lie in the same plane, we're going to use the scalar triple product to find the volume of the parallelepiped. So we're going to do these vectors. So I'll call that one, the first one A, that's our vector PQ, and that's 1, 4. So I'm taking from Q, I'm removing 1 from the X and the Z component, so that's 1, 4, 5. For B, that's going to be P to R, so that's this one. C will be this one. And so again, tip minus tail. So R is 3, negative 1, 2. I'm going to take 1 away from its first and last component. And C is P to S. And I'm going to take 1 away from its first and last component. So there's our 3 vectors, A, B, and C. And now we'll take the triple product of them. We'll find the volume of the parallelepiped that they make. And so this scalar triple product, it's most easily done by setting all the vectors up in a matrix like this. And then, oh, sorry, that's B cross C. And then taking the determinant. So that's how we can do the scalar triple product with our memory device for the cross product. And so this is going to be our 1 times this determinant here. So that's 1, and then negative 7 minus 2. And then we get a minus 4 times the determinant of the next piece, which is 2 times 7, which is 14, minus 5, and then plus 5 times the determinant of the bottom left 2 by 2 matrix, which is 4 plus 5. And so this works out to be negative 9. And then we get 14 minus 5 is 9. So that's a negative 4 times 9 plus a 5 times 9. So I've got negative 5 times 9 plus a 5 times 9. So that's 0. And therefore, since the volume of the parallelepiped that these 3 vectors make has 0 volume, it means that all 3 vectors live in the same plane, or in other words, all 4 points are coplanar. Therefore, the 4 points are coplanar. Okay. So this is the kind of way we're going to be using dot products and cross products. Is we're going to allow, it's going to allow us to determine spatial configuration. So how things are related to each other. Do they live in the same plane? Do they not live in the same plane? If they don't live in the same plane, or if maybe a point doesn't live on the line that another 2 points do, how far away is it going to be from that line? That's sort of leads into our last example. Yep.
If the determinant is not equals to 0, then they don't lie in the plane. Then they're like, okay.
That's correct. Yeah. If the determinant is non-zero, so it's going to be some positive, well, it's going to be some value in this case, and then when you take the absolute value of it, it'll be positive. It means that the parallelepiped does have a volume, in which case the 3 vectors don't live in the same plane. And so the 4 points also don't live in the same plane. Yeah, that's a good observation.
All right. Thank you.
You're welcome. So this last one says, let P be a point not on the line L that passes through Q and R. So the idea is we got these points Q and R, and I got a point P that doesn't lie on them. So something like this. The question is, how far away is that point P from the line? So the distance will be measured sort of, you take a perpendicular line to the line itself that passes through the point P, and that would be the distance that P is to the line. In other words, it's the closest distance you would have to travel to get on the line. We'd like to know how to compute that. And that's what this formula is given in the question. So let's see how we would actually compute that. So the first thing we would do is we would construct some vectors, since the vectors are the objects that we're able to work with using cross products and dot products and the like. So I would construct a vector that points in the direction of the line. And then I'd construct another vector from any point on the line out to P. I'll just pick Q to be that one. So that's our vector B. It doesn't matter what that vector B is. I could have gone from R to P, or I could have picked an arbitrary point on the line and just drawn it out to P. The only thing that matters is once I've constructed that vector that goes from a point on the line out to the point P, in other words, that vector B, that is going to allow me to compute the distance, because now I can construct this vector, which maybe I'll call W. And W is just going to be the vector B minus the projection of the vector B onto A. So in other words, we can compute it. Whatever the vector B was, we can always compute W, because the vector is going to be obtained by sort of taking this difference in this way. Okay, so now we want to compute the length of W. So we want the magnitude of W. Let's just consider the right triangle. So by the right triangle, so it'll turn out that this is actually quite a straightforward and computation that involves very little steps. So by the right triangle, what is the magnitude of W? Well, the magnitude of W is, if I just throw an angle in here, it's just given by the magnitude of B times the sine of the angle between B and A. Okay, that's just using our right triangle and trigonometry. So magnitude of B times sine theta is the hypotenuse times the sine of the angle gives me the length of the leg on the opposite side of the angle. That's all I'm doing here. But we also have that sine of theta can be related to the cross product. That's A cross B in magnitude over the magnitude of A, magnitude of B. So that's using our relationship between sine of the angle and the cross product. And that gives us our result, because now the magnitude of B's cancel. And so that's the end of our argument. And so that means if I want to work out the value of the distance from a point to a line, I just need to know the vector in the direction of the line and any vector that goes out to the point, and I take the cross product and divide by the length of the vector in the direction of the line. All right, so that's it for this section. I'm going to stop the recording now.